Welcome to the first lesson of Chapter 6, Applications of Integration. In this chapter, we're going to be looking at how to find the area between two curves and how to take an area and rotate it around either the x or y axis or an external axis that is given to us to create 3D objects and find the volume of those 3D objects. So today we're going to be looking at just areas between two curves where we have an upper curve and a lower curve. Okay, so if f and g are continuous on a closed interval a to b, and if f is greater than or equal to g, meaning one of your functions is smaller than or equal to the other function, for all x in your interval, then the area of the bounded region is the integral from a to b of f of x minus g of x. So in other words, you have this area that is bounded between your two curves and starts at a certain endpoint and ends at another endpoint. In this case, we're calling those A and B. So you have four sides of your object, okay? And you have an area in between. To find that area, you can take the integral from A to B of the upper curve minus the lower curve. So the first one should always be your upper curve. So the top one. And the second one that you are subtracting from that is always your lower curve, or the bottom one. And so instead of having bounded by the x-axis like we've seen before, you're bounding your area by a second curve. So let's try some. We are going to find the area enclosed by the following curves. So it gives us an a value and a b value. We need to figure out which ones are upper curve and which ones are lower curve in order to figure out what the area is going to be. Okay. It also is helpful to figure out where the curves intersect, because sometimes what will happen is you will have some sort of intersection point within your upper and lower bounds where you need to switch which curve is the upper and the lower and break your integral up into two pieces. So it's always helpful to draw a little picture and figure out which one's upper, which one's lower, and where do they intersect with each other if they intersect at all. Okay. So let's draw ourselves a little picture here. It doesn't need to be perfect, but it should be fairly accurate. So if we have y equals x squared, it's going to look something like this. And if we have y equals x plus 2, we have an intersection of the y-axis and our x plus 2, a y-intercept at 2, and then this should have a slope of 1. So if we have some numbers here, let's add a 1 and a 2 and a -1 and a -2. We'll add 1, 2, 3, 4. Okay, so if we go up 1 over 1, we're going to end up about here. Up 1 over 1, we should end up on our parabola. Down 1 over 1, we should end up here. And maybe I should fix my I want make it a little bit more accurate. Okay. Down 1 over 1, intersect, down 1 over 1. So this is our y equals x plus 2. And we can figure out algebraically, if we prefer, where they intersect instead of using the graph. But basically, if they intersect somewhere in your closed interval, a to b, you need to pay attention and see if then what happens is they switch which one is upper and lower. So in this case, our upper is x squared and our lower is x plus 2. Okay. Our region goes from x equals 0 to 1. And that is where our shaded area would be. Okay. To figure out where they intersect, this would be where x squared equals x plus 2, or x squared minus x minus 2 equals 0, or x minus 2, x plus 1 equals 0, or x equals 2 or -1, which is what we showed on our diagram. So they don't intersect in our intervals, so we're okay to just keep going with the idea that x squared is our upper and x plus 2 is our lower. So the area that is enclosed is going to be the integral from 0 to 1, lower to upper, of our upper function, x squared, minus our lower function, x plus 2, and then dx. So if we think about this in terms of area, basically what we have is we have these little rectangles, okay? We have little rectangles that are drawn underneath the upper. So essentially, if I drew my little rectangle, it would look something like our lower. Sorry, I did upper and lower in the backwards. Upper is x plus 2, and lower is x squared. I apologize. Okay. So our upper is x plus 2. So if I were to draw rectangles, I'd have something that looks like this underneath our straight line. And then what we're doing is, because the area under the curve between the upper and lower does not have this chunk here, we're basically subtracting that chunk, which is the area under our lower curve. Okay. So when we do this, we can just do our antiderivative straight away. We get 1/2 x squared plus 2x minus 1/3 x cubed from 0 to 1, which gives us 1/2 plus 2 minus 1/3 minus 0, or 3/6 plus 12/6 minus 2/6, which gives us 13/6. All right. The next one, we're using the same two functions. So I'm going to draw these two functions again. And we know that these two functions intersected at -1 and 2. Now, the difference for this one is there is no upper or lower bound. Okay. This means we're looking for the entire area and the intersection points are necessary. Okay. So in this case, our entire area is this chunk here, and we need to determine what the upper and lower bound will be. So if no upper or lower bounds are given, determine the intersection points these will be your bounds. In other words, we're looking for the area that is enclosed by the two functions. Okay, so completely enclosed by those two functions. There are no extra lines that are enclosing our shape. Okay, so if we do that, then we're going to have the area is going to be the integral from -1 to 2. Our upper function again was x plus 2 minus our lower function x squared, and we're integrating that with respect to x, which gives us again 1/2 x squared plus 2x minus 1/3 x cubed. We're integrating from -1 to 2, so we're going to have 4/2 plus 4 minus 8/3 minus 1/2 minus 2 plus 1/3, which gives us 6 minus 8/3 minus 1/2 plus 2 minus 1/3, or 8 minus 9/3 minus 1/2, which is 8 minus 3 minus 1/2, which gives us 5 minus 1/2, which gives us 4.5, okay, or 4.5, or 9/2. All right, so we're going to try one where we're going to need to switch which one's upper and which one's lower partway through, reading our graph left to right. And that's going to mean that we're going to have two integrals that we need to consider, because as soon as the upper function is no longer your upper function, what that means is that your integral no longer pertains. So if you find the point at which the switch happens, that is going to be where your bounds are going to change and your integral is going to change, and therefore you need a new integral. So let's try this one. So we've got x equals y squared and y equals x minus 2. So let's go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. Okay, so if x equals y squared, a reminder that that's like your sideways parabola looking thing. Okay. The other way of writing this would be y equals plus or minus root x. And the other function that we have is x minus 2. So we can see that our enclosed area here, we don't have an upper or lower bound given to us. We must determine those. Okay. We want to figure out where these intersect. That can be x values or y values. I would pick a y value just because, for example, when x is 1, there are 2 values. When x is 4, there are 2 values. So I would choose to find the y values at which these intersect. So I get y plus 2 because here you'd have y plus 2 equals x. So then our two x's are equal. So you get y squared minus y minus 2 equals 0. Y minus 2, y plus 1 equals 0. Y equals 2 or negative 1. So when y equals 2 or negative 1, so here's where y equals 2 and here's where y equals negative 1. That's what we had found. And we drew it. So really the algebra is just making sure that you haven't done something wrong, and it also then makes it so you don't have to graph perfectly. You can just sketch and then algebraically find where they intersect. Okay. Now we notice here that we have hopefully two different chunks of our graph. We have a chunk of our graph right here where the blue one is clearly over top of the purple one. And we have another chunk of our graph right here. Oh dear. Sorry, let's draw my axes back in and draw the other half of my parabola back in. We're going to need that. Our other chunk of our graph is here, where the purple one isn't even in play. Oh, sorry, the blue one, purple one isn't even in play. The blue one is completely containing the area. So we have this kind of top part of the blue one and bottom part of the blue one containing our area here. Okay. So what that means is from 0 to 1, when x is 0 to where x is 1, the blue one is containing this red area, meaning the upper portion of the blue graph is the top upper function. The bottom portion of the blue graph is the bottom or lower function. From x is 1 to x is 4, we have the upper function being the blue one and the lower function being the purple one. Okay. Now, hopefully we'll notice that if we look at the upper function portion of the blue graph, that would be where y is equal to positive square root x. And the bottom function of the blue graph is where y is equal to negative square root of x. So we're going to have two portions of our integral. We're going to have the area is equal to the integral from x is 0 to 1 Our upper function is root x minus our lower function, which is negative root x with respect to x. And then we need to add on this green portion, which is from x is 1 to 4. Upper function is root x. Lower function is when y is x minus 2. And again, with respect to x. And now we can find these integrals, simplify, make it look a little nicer. So we're going from 0 to 1. We'd have 2x to the 1/2 dx plus 1 to 4. We're going to have x to the 1/2 minus x plus 2 dx. So we should get here x to the 3/2, and then we should have 4 over 3 from 0 to 1, plus we'll have x to the 3/2, and then we should have 2 over 3 minus 1/2 x squared plus 2x from 1 to 4. So we're going to get 4 over 3 times 1 minus 0, this first one, plus we should have 4 to the 3 over 2 times 2 over 3 minus 1/2 times 4 squared plus 2 times 4 minus 2 over 3 times 1 minus 1/2 times 1 plus 2 times 1. So we're going to get 4 over 3 here, plus we get 2 cubed, 2 to the power of 4, so 16 over 3 minus 8 plus 8 minus 2 over 3 plus 1/2 minus 2. So 8s can cancel. So we get 20 over 3 minus 2 over 3 gives us 18 over 3 plus 1/2 minus 2, which gives us 9. Wait, sorry. 6 minus 2, sorry. We get 4 plus 1/2, which gives us 4.5, or 9 over 2, or 4.5. The key ideas from this section: if you have an a and a b value, you need to figure out what your upper and lower function are. You subtract your lower from your upper in your integral. If they switch, you need to write a second integral. Your first one would be from a to wherever they switch. Your second one would be from wherever they switch to b, and your upper and lower functions would switch within your integrals. If you have no upper and lower bound, that means your area is completely enclosed by the two curves. You need to find an upper and lower bound. To do that, you need to find the intersection points. And it could be that you are doing that and that your upper and lower are switching partway through. So you could have something, for example, that looks like, I don't know, like this and like this. You might not be given any upper and lower bound. This would be your A, this would be your B, and you have this other point in the middle, C. So you'd have this one here where your black one would be the upper curve and your blue is the bottom. And then this extra point here where the blue is the top and the black is the bottom. So you can have it where it switches and you need to find the intersections. It's very helpful to sketch yourself a little graph and use that. It does not need to be perfect. You can use algebra to figure out your intersection points and helpful points on your graph, but the sketch will help you determine which one is the upper and which one is the lower bound. And that is all.